In this lesson, we're going to talk about functions, specifically how they describe change. So, let's start off with a relation. A relation is basically just a collection in which you're taking data from two different sets and correlating them together, and usually we write these things as ordered pairs. But a function is a special kind of relation. In a function, we consider one set of coordinates as the input and the other set as the output, and we insist that when you take an input, you get exactly one output. So, some examples of functions. Height can be a function of age. So if you have taken measurements of a person's height given their age, then when you plug in their age into the function, you can find out their height. Precipitation can be a function of the date. After you collect the data, you put in the date, you find out the precipitation. Cost to mail a package is a function of its weight. So you put in the weight of the package, and then you can take the function to tell you its cost. So, let's take a look at these two. Which of these models an actual function? So in this first example, 1 maps to 10, 2 maps to 20, 3 maps to 30, and 4 maps to 40. The second example, 1 maps to 10, 2 maps to 20 and 30, 3 maps to 40, and 4 maps to 50. So the definition is that every input has exactly one output. So with that said, this one cannot work because of this 2 mapping to both 20 and 30. That means that our correct answer must be this one, because this one has each input giving exactly one output. Let's look at another example. So we've got a table of women in the U.S. Senate and how many there were each year. And then the second, we've got a sample of women's ages and the number of children that they have. So one of these is a function, and one is not. So let's take a look at this second one. The one piece of information that I'm looking at that's a little bit odd to me is the fact that there is a 31-year-old and another 31-year-old, and the first one has 3 children, but the second one has only 2 children. So if you treat this as a function, it would insist that given an age as an input, you can output the number of children. But right here, 31 as an input does not give you a unique output. It could give you 3 or 2. So let's make a note of that. An age of 31 has 2 possible outputs. So with that said, let's take a look at the first table. So in the first table, we don't see any duplication among this first column. It's all different years. Now there's definitely some duplication of numbers on the right column, but the fact of the matter is each year has a unique number associated with it. The number 1997 has all the same values of just 9. When you say I am inputting 1997, the output is there were 9 people. There's no ambiguity there. When you say the input year is 1999, the output is 9 women. Again, no ambiguity there. So it's okay for an output to repeat because it's still saying this input brings 1 output. So with that said, this is the correct answer. And let's write this down. Each year has exactly 1 value for the number of female senators. So if we are to talk about these functions, we often use the phrase, y is a function of x. What this means is for a value of x, which we're calling the input, it corresponds to exactly 1 value of y, which we're calling the output. So again, the phrase is y is a function of x. So if y is a function of x, x again is our input, and we call this the independent variable because we get to choose the input. And y is the dependent variable, and that this y value is going to depend on which value of x that we choose. So let's take a look. So in this table, we want to determine if y is a function of x. And so if we look at this, it appears that the x's do not repeat, which I mentioned in the last slide is a good thing. So even though we have a repeating output, the fact of the matter is that 1 has only one output, 22. And 2 has only one output, 22. So is y a function of x? Yes. And let's explain why. Every input corresponds to exactly one output. So let's label our variables. The independent variable is x, because that's our input, and the dependent variable is y, because that's our output. So next, is x a function of y? That's saying if we choose y as the input, can we have x as an output? So now here's what I was talking about and where this becomes a concern. Y is a function of x, yes. But to ask whether x is a function of y, no, it's not. If you were to take 22 as an input, you wouldn't know which output to pick. Would you pick 1 or would you pick 2? We don't know. So therefore, no. The input of 22 corresponds to two outputs, namely 1 and 2. Net change. So net change is something that we talk about for functions. And so the net change in the variable y, we often look at the inputs as a and b, but we do insist that when we're talking about this, that a is the smaller of the two inputs. And so what we do is we take the value of y at a and subtract it from the value of y at b. So this is in some ways the function value at b minus the function value at a. So this value is an overall change. It's kind of an averaging value. It doesn't give you information about what happened in between, but simply what happened overall. So first off, let's explain why y is a function of x. Again, looking at our years, I see no repeats, so I'm not going to really pay attention to what the numbers on the right are. I have y as a function of x because each year corresponds to a dollar amount. Let's write that down. Each year corresponds to a dollar amount. So now let's find this net change in gas price. So between 1997 and 1999, we've got $1.33 in 1997 and $1.36 in 1999. So again, you take the function value of the larger, which is $1.36, and subtract off the function value of the smaller, which is $1.33. And so I get a change of only $0.03. So that's a 3-cent change in gas price during that time period. But one thing you'll notice is that if you were to look at the data on a more larger scale and look at everything in between, there was a little bit more going on than the gas price going up by 3 cents. It went down a lot and then back up to near where it was before. This is what happens when you take a net change. Sometimes because it's a piece of summary data, you don't realize that something may have happened in between. Let's do the same thing for 1996 to 2006, the entire data set that I have here. So again, take the one from the larger number, the $2.81, and subtract off the original $1.32. So when I do that, I get $1.49 difference. That's a fairly significant change in gas price over 10 years. No wonder the outcry that has happened because of gas prices. So let's consider this equation, x squared minus y. So when we're talking about equations, how do we know that equations represent a function of x? Well, one way to do this is to look at how the values are calculated. So, if y is a function of x, that means that for any value of x, I can find a value for y. The easiest way to do this is to solve for y in terms of x. So what I'm going to do is I'm going to copy down this equation, and I'm going to solve for y by adding y to both sides. So I get y equals x squared. And now I think it's clear that if I plug in one value of x, I'm only going to get one value for y. So let's write that down. Each value of x produces one value of y. So, is it a function of x? Yes. How about the other way around? Does the equation represent x as a function of y? Let's look at it from the other direction. X squared equals y. And then let me solve for x by taking the square root of both sides. And remember, when I take a square root, I need a plus or minus. Now this looks completely different from what I did earlier. So you'll notice that if I plug in a value for y, I'm going to get two values for x. That is not a function. So let's write this down. One value of y can produce two values for x. That means it is not a function. So, if we have an equation that represents a function, we can do exactly what we did in the previous slide. We can write it in function form. So when we write it in function form, we're going to be solving for the dependent variable, and then we'll put independent variables, there may be more than one, on the other side. So let's do something similar for this equation, a little bit more complicated looking. So does the equation represent y as a function of x? Well, let me start out by attempting to solve for y. So I'm going to get, subtracting 5x from both sides, I'll get 3y squared equals 7 minus 5x, and then dividing by 3, I have y squared equals 7 minus 5x over 3, and so when I take a square root, I'm going to again get that plus or minus bit of 7 minus 5x over 3. Now we don't like this because again there's a plus or minus, so rather than write all the words again, let's just say no, it's not. We can see that in order to solve for y, you end up having to get two values for y every time you plug in a value for x, pretty much. Does the equation represent x as a function of y? Let's try this instead. So 5x plus 3y squared equals 7. We could subtract 3y squared from both sides, and we get 5x equals 7 minus 3y squared. Divide by 5, and you get that x is equal to 7 minus 3y squared over 5. Now in this case, plugging in a value of y is just going to give you one value of x. So yes, this is a function. So x is a function of y here, but y is not a function of x. Let's do another one. So, in the previous example we had some squares floating around and that caused some trouble. So what does happen if you have cubes floating around? So first off, let's show that p is a function of v. Now I think this is almost clear because p is already solved for, but let's just write something down. Substituting in a value for v will give one value for p. So with that said, this is a function. So, p being a function of v means I can calculate the net change. So as the wind speed changes from 7 to 10 kilometers per hour, let's find the net change in power that this windmill is generating. So what I'm going to do is let me label these A and B, and I'm going to substitute in B first. So 15.6 times 10 cubed minus 15.6 times 7 cubed is going to give us the net change in power. So let's see if we can calculate this. This is 15.6 times 1,000 minus 15.6 times 343. So I get 15,600 minus 5,350.8. And so finally when I subtract those, I get 10,249.2. And my units are watts, which is usually represented with a capital W. So now what if we go the other direction? If we want to try to express v as a function of p, we will need to solve for it. So, let's start out by dividing both sides by 15.6. Then we get v cubed equals p over 15.6. And if I take the cube root, I get that v is the cube root of p over 15.6. And let's just make the comment, this is a function of p. So with that said, we can now do the same thing we did last time. We've got 1,000 watts to 10,000 watts, and we want to find the net change in wind speed that will accomplish that. So let's plug these values in. We've got the cube root of 10,000 divided by 15.6 minus the cube root of 1,000 divided by 15.6. I get 8.62 for my first value, and then for my second value, I get 4.00, and that is a rounding to 2 decimal places. So my final answer is going to be 4.62, and this is in kilometers per hour. So here's another way we can look at functions. If we look at it from a graph, there's a very easy test to determine whether something's a function. What we do is we simply use what we call the vertical line test. The vertical line test says that you have a function from this graph if no vertical line intersects it more than once. Another way to say that is every vertical line intersects it exactly one time. And so as you can see, this first one is definitely a function, because every vertical line intersects the graph once. But in this example, this vertical line intersects the graph twice. So let's say not a function. And let's give an explanation for this also. So for the first one, we'll mention that every vertical line intersects the graph once, and for the second one, this line intersects the graph twice. So for this reason, the first one is a function, but the second one is not. Next example. We have a cup of coffee with a temperature of 200 degrees Fahrenheit that's placed in a room with temperature 70 degrees. And so we've got this cooling function here that shows how the temperature of the coffee changes after t minutes. So to make a claim that this is a function of t is actually pretty straightforward. I'm not going to draw any lines on here because of the second part, but notice that every vertical line passes through the graph once. That's why we have a function of time here. So let's find the net change in temperature during the first 10 minutes of cooling. So if we look at the values of the function, in this case we're looking at a equals 0 and b equals 10. That's the first 10 minutes of cooling. So at 10, remember we always do b first, it looks like the temperature was 150 degrees Fahrenheit, and at 0 the temperature was 200 degrees Fahrenheit. So we get negative 50 degrees Fahrenheit is the total change in temperature in the first 10 minutes. Let's look at this scatter plot, as it's called. So we've got a local campaign surveying voters on their frequency of voting, and we're looking at the age of the voter surveyed and how many times they have participated in an election. Use the graph to find the outputs that correspond to the input 40. A 40-year-old person, it looks like we've got one who voted once, and another one who voted, looks like 5 times. So let's write that down. One person of age 40 voted once, the other voted 5 times. So now let's list the ordered pairs for this. So with this input 40, we're looking at 41 and 45. This is intended for us to now see that this graph is not a function of x. What it is that if you can find 2 ordered pairs with the same x-coordinate and different y-coordinates, we can immediately say it's not a function of x. Why? Here's your vertical line. These 2 points are a place where a vertical line can cross twice, since they have the same x-coordinate. Notice from that previous slide that because we were talking about data that didn't represent a function, we can't really talk about net change. Now there's something called a regression line, but we're not going to talk about that right now. So following the thought process of the previous problem, let's look at this example where the vertical line test is being used in this graph. So what we can do is we've got this equation x equals y squared, and since we can see these 2 points where the vertical line is passing through, we could actually just make the claim, here's your 2 points. We've got 4, 2, and you'll also notice 4, negative 2. So one way to claim that a graph is not a function, or anything is not a function, is to find 2 points with the same x-coordinate and different y-coordinates. So let's finish this off with the 4 ways that we talked about to represent a function. So you can talk about a function verbally, numerically by a table, symbolically with an equation, or graphically by drawing an actual graph. And we've worked with all of these today. So let's take a look at this verbal description of pizza parlor charges. Verbally, we have the pizza parlor charges $10 for their plain cheese pizza, and then they charge $1.25 for each topping on top of the pizza. And so we do have a function of the number of toppings that creates the cost of the pizza. Symbolically, let's let x be the number of toppings, and y is the cost of the pizza. So y is going to equal $10 for the original price, and then $1.25 for each additional topping. So this is our symbolic way to represent this. Numerically, we can also write this in the table. At 0, this was the original $10 pizza. At 1, you're going to add $1.25, so that's $11.25 for the pizza. For 2 toppings, you'll add another $1.25, so that's $12.50, and so on. $13.75 and $15 for a 4-topping pizza. With this information in hand, we can even draw a picture pretty well. So let's do a little bit of a jump on this picture. Let's go by starting at 10 and going up by 2 each time. And we'll go by 1s on the x-axis. So if we draw a graph of this data, at 0, the pizza costs $10. At 1, the pizza is $11.25. At 2, we have $12.50. At 3, we have $13.75. And at 4, we have $15. So the more toppings you put, the more the pizza costs, which should make sense.